Hi, this is Mrs. Hanson. Thanks for listening. This is an optional AP Chem video about limiting reactants in solutions. So this is the exact example that was in the notes provided, but I want to make sure we talk about how exactly it works. So the problem said we had 50 mils of 0.2 molar silver nitrate reacting with 25 mils of 1 molar sodium chloride. All right, so we mixed the two and a double replacement reaction took place. So the silver hooked up with the chlorine and we made this precipitate according to the solubility rules. All right, so anytime we do a problem where I give you amounts of one reactant and amounts of the other reactant, by golly, you have to confirm which one is the limiting reactant. So that's why the first step, some way, somehow, you have to figure out the amounts of each reactant. So I went with the moles of silver nitrate first. Molarity, moles per liter times the volume converted to liters. This is how many moles of silver nitrate I had. Did the same thing with the sodium chloride. Took the molarity of sodium chloride, multiplied it by the volume converted to liters. Okay, so now I got the moles of both reactants. And that's going to be useful throughout the entire problem. So that's why I like to calculate that first thing. Now in this problem, because everything is a 1-to-1-to-1 ratio, I can clearly tell which one is a limiting reactant. I'm going to run out of sodium chloride before I do silver nitrate because there's less sodium chloride. Now, if your reactants are not in a 1-to-1 ratio, you can do exactly what you did in CP Chem, and it is a wonderful process. Go ahead and take your moles of silver nitrate and convert it to product. That would be, you can pick one, but I would go with the silver chloride. Go ahead and convert to silver chloride. So for every 1 mole of silver nitrate, I have 1 mole of sodium chloride. Sorry, silver chloride. And then do the same thing with the other reactant. Take this much reactant, see how much product you can make. And then you pick the lower number, okay? That's how we did limiting reactants way back when last year in chemistry. Okay, but if it's real simple and you can just tell which one's a limiting reactant by looking at it, it's okay. All right, so that's our first step. And that's how I came up with these pictures. I knew that I had silver nitrate. I had more silver nitrate than I did sodium chloride. And of course, this represents the volumes of the two solutions, 50 milliliters versus 25. Notice that they're both strong electrolytes, so the ions are dissociated. All right, sorry about that bing bong. That's like emails. I don't know how to turn that off. Maybe you can help me. Nonetheless, this is what it looks like when the two solutions are mixed, but before reaction. So I wanted you to note that if you mix a 50 milliliter solution with a 25 milliliter solution, your new volume is 75 mils. And that's going to be really important to apply that later on in the calculations. Here's the most important picture. If you can visualize it, then the math should make sense. Okay, if I go back to this picture, if I make as much silver chloride as I possibly can, okay, there's one silver chloride, there's another silver chloride, ran out of chlorine, and which supports the fact that the sodium chloride was a limiting reactant. So I'm going to make as much precipitate as I absolutely can. So these guys are just that white powder that basically settled to the bottom, my precipitate. Okay, notice that there's no chlorine left. Okay, but there is some silver left, and then I got my nitrates and my sodium. Okay, so first thing, if the question asks, you can very easily calculate the mass of the precipitate. So always base that off the limiting reactant. Okay, whatever you're going to run out of, that is going to determine how much product you can make, how much precipitate in this case. So I took my moles of sodium chloride that I knew I was going to use up, that I know I'm going to run out of, did a mole ratio to see how much silver chloride I can make, and then converted that to mass. So this is the mass of precipitate that would be at the bottom. All right, now for the rest of this problem, we need to calculate the concentration of all the ions that are left in solution. The easiest one to do, always, is for precipitate reactions, one of your ion concentrations is going to be 0 molar. There's not going to be any of that ion left swimming around in solution. And of course, it's pretty obvious to see from the picture that that's going to be the chloride ion concentration. Chloride ion concentration is going to be 0 molar because every single one of those chlorine atoms is now locked in the precipitate. It's totally used up. So the limit, knowing which one's a limiting reactant is going to tell you which ion is locked in the precipitate and no longer aqueous. Now, as for the other ions, let's see. What about the silver ions? You know what? That will always be the hardest ion to figure out Why? Because part of the silver is locked in the precipitate. The rest of the silver is aqueous. I need to figure out how much of those silver ions are left over in solution. So the leftover ion is always the tricky one, is always the hardest one to figure out. Now, as for the rest of the ions, let's see. We got the nitrate, and we got the, what is the other one? Sodium, sorry. Whew, I'm losing it. We got the sodium. Sorry about my handwriting. My airliner, of course, is not working very well. So we got the nitrate and the sodium ions. Well, if you go back, what was their role? You have to go back to the balanced chemical equation. If you go ahead and net ionize it, okay, go to net ionic equation, you'll see that the nitrate cancels out. Sodium cancels out. Why? Because they're spectators. So you know what? If I look at my picture, I originally had 1, 2, 3, 4, 5, 6 nitrate ions swimming around in solution. In my final picture, 1, 2, 3, 4, 5, 6, I still have 6 nitrates swimming around in solution. Whatever moles of nitrate you started with, they're still there at the end. The only challenge is that now those nitrates are spread out over 75 milliliters instead of being squished into that original 50. So you have a dilution effect. Okay, so the spectators, these two guys right here, should be pretty easy. If you get the moles of the nitrate, you just got to divide it by the new volume. Same thing with the sodium ions. Okay, so let's sort of look at the details here. Now, I told you that figuring out the leftover ion is definitely the hardest part. There's a lot of different ways to do it. In the notes, always though, you got to start with whatever the limiting reactant is. So if the sodium chloride is a limiting reactant, I'm going to say to myself, well, gosh, how many silver ions do I actually need to completely react with my limiting reactant? So I took my moles of sodium chloride and the silver nitrate are in a 1-to-1 ratio. And for every 1 mole of silver nitrate, I need 1 mole of silver ions. So I would need this many moles of silver plus. That's what's going to be locked in the precipitate. There's some different ways to do this. If you went ahead and started with the precipitate instead, so I know I'm going to make 0.00250 moles. This is painful to watch, I know. Okay, of silver chloride, right? So you can start with the original amount of sodium chloride, the reactant that you're going to run out of, or you can start with the amount of precipitate that you know you're going to make. Sometimes this is a little easier. So if I know I'm going to make this much precipitate, well, for every 1 mole of that precipitate, sorry, almost there, we're getting there, I would need, again, 1 mole of Cl minus. Okay, and you know what? Sorry, not Cl minus, 1 mole of Ag plus. You get the same answer, okay? But this took like only 1 step. Now, why is this step or this step respectively important? Just remember that in this compound, there happens to be 1 silver for every 1 silver chloride, or 1 silver for every 1 silver nitrate. But that's not always going to be the case. What if your compound was not silver nitrate, but rather, you know, silver sulfate? Then, you know what? For every 1 silver sulfate, you'd have 2 silver ions that you would need to be locked in the precipitate. So the bottom line is that you got to make sure you go from the substance to the ion that you're interested in. So this is a very important step. Doesn't affect the math in this problem, but in some of the other problems you're going to do, like if this was involved, you'd have a 2 up there. That would definitely affect your numbers. Okay, so needless to say, some way, somehow, you have to figure out how much silver is going to be locked in the precipitate. This is what's needed to react with the limiting reactant. Now you got to figure out how much silver you had available. So notice that this 0.01 goes back to the original problem. This is how much silver nitrate I originally had. Okay, well, for every 1 mole of silver nitrate, I'm going to get 1 mole of silver ions. Again, this is important, especially if it's not a 1-to-1 ratio. So this is how many silver atoms or ions are available. Okay, so you take these two numbers, subtract the available silver ions minus the silver ions locked in the precipitate. That difference, this guy right here, is the amount of silver ions floating around in solution. So if I go back to my picture, that would be these guys right here, aqueous. Okay, so I basically took the 1, 2, 3, 4, 5, 6, the total number of silver ions, and subtracted 2, 1, 2, what was locked in the precipitate, and that told me what was left over. So that's a lot of steps. Bottom line is this is moles of silver ions floating around in that leftover solution, and I need concentration. So I need to divide it by that total volume. So finally, that's where the 75 mils comes into play. So that is the ion concentration of silver ions left over at the end. See, you can do that, no problem. As for the spectators, a lot of different ways to do it. The bottom line is for the spectators, you always got to go back to your original data. Where did the sodium come from? The sodium came from the sodium chloride. So that being said, this was my original moles of sodium chloride. For every 1 mole of sodium chloride, there's 1 mole of sodium. Again, extremely important step. Not so much in this problem, but in future problems, like if there were 2 sodiums in the formula, okay? So there's my moles of sodium plus. And then you need to get the concentration of sodium plus, Na plus, so you have to divide it by the new volume, okay? Same thing with the nitrates. If you have 0.01 molar silver nitrate, notice that came from the original data, from the original information. For every 1 mole silver nitrate, there's 1 mole of nitrate. Take that number, divide it by the total volume. Okay? Just to give you an example, real quickly, in case you're confused about what I mean. What if you did use sodium sulfate? What if that's where your sodium came from? Okay? Then if you had like a 0.1 molar to 0, or 0.1 moles of sodium sulfate, Na2SO4. That's really ugly. I apologize. But there would be, for every 1 mole of that whole compound, there would be 2 moles there would be 2 moles of sodium ions. So do you see how that would actually change the math a little bit? Okay, so you just got to be really aware of that step right there. All right, other than that, I hope that helps. Please don't hesitate to come in and get some extra help. And keep in mind that there's some different ways that you can think about this a little bit. So if you modify the rules, as long as it makes sense to you, then it makes sense to me. Okay, and that you're getting the right answers all the time. All right, thanks for listening. I hope this helps. Come in and get help from your teachers, please. Have a great day. Bye.